This video is meant for Mrs. Rose's AB Calculus class, and it is the introduction to Unit 6, and we're going to start with the area of a region between two curves. In class today, our agenda is to do a journal prompt, and then we're going to look at the area of a region between two curves, and then we are going to do a matching activity. And our homework, we're going to have a partner activity that I need you to prep for, as well as some differential equations and slope-field multiple choice questions. Alright, so our goal is to find the area between f of x, this quadratic, and g of x, this linear function, between the values of x equals -2 and x equals 0. So basically I want this area. Okay. And if you remember from before when we looked at area for the first time, we are going to take definite integrals. So we're going to look at the area underneath f of x. It goes all the way to the x-axis. And we write that integral as the integral from -2 to 0 of f of x dx. And what we want to do is we want to get rid of the area that's underneath g of x. So we're going to subtract the area under g of x on the same interval. So to get just the area in the middle, we're going to have the integral from -2 to 0 of f of x minus g of x. When you do something like this, where you have one function, f of x minus g of x, you need to assume that this is your higher function, and g of x is going to be your lower function. So you're going to have the upper function first, and you're just going to subtract the lower function. These formulas assume that f of x is greater than g of x over the whole interval. Okay, so we're going to look at the area bounded by the graphs y equals x squared plus 2 and y equals -x. So we've got the parabola x squared plus 2, and I've got the line y equals -x. And we're looking at the interval from 0 to 1. 0 to 1. So I'm going to set up the integral. The upper function is going to come first, my quadratic, and I'm going to subtract the lower function, -x. Then I'm going to do distribute the negative. So I've got negative, and a negative becomes positive. So the integral from 0 to 1 of x squared plus x plus 2 dx. And now I'm going to take the antiderivative. Remember, you're adding 1 to the exponent and multiplying by the reciprocal. So I have 1/3 x cubed plus 1/2 x squared plus 2x, and we're evaluating at 0 and 1. 1 gets plugged in first. So I have 1/3 plus 1/2 plus 2 minus 0, and this equals 17 over 16. That number represents the area of the region bounded by all of these functions between 0 and 1. Okay, so on this one we have the quadratic 2 minus x squared and the linear function y equals x. We don't have any x values. So when you have no x values, we want to look at just the area where they have in between their intersections. So we can easily see from the graph that the intersections are -2 and 1. But if you don't have a handy graph that's easy to read, finding the intersections is easy to do algebraically. All we need to do is set the two functions equal to each other. I'm going to move everything to the right-hand side so I can get something that's factorable. My factors are x plus 2 and x minus 1. So when we solve for x, we get -2 and +1. So these are the intersection points. Then we have to figure out which function is higher. It's, again, easy to see by the graph that the quadratic is higher. If you don't have a handy-dandy graph that's easy to read, all you have to do is plug in a point on the interval between -2 and 1 and see which one has the higher value. G of x, or the quadratic, clearly does, so we're going to put g of x first in our definite integral. So for the third thing, we've got our definite integral of the negative 2 to 1. The quadratic comes first, and we're subtracting the lower function, dx, and then we need the antiderivative, evaluated at negative 2 and 1. Plug in 1 first, plug in negative 2, and the area bounded by both functions is 9 over 2, or 4.5, or 4 halves. At this point, maybe you can pause the video and try this one on your own. Press continue when you're ready to check your answer. This one's harder than the other ones were before. On this one, we have 3 intersection points. When you set the two quadratics equal to, well, cubic and quadratic equal to each other, and factor, we have 3 intersections, 0, negative 2, and positive 2. So when we have those, we need to figure out which function's on top for each interval. One from 0 to negative 2 to 0, and the second from 0 to 2. So again, a handy-dandy graph is easy to check, but if you don't have a graph, plugging in numbers on the intervals is easy. So I'm going to plug in negative 1 and 1. When you plug in negative 1 into my f of x, you're going to get negative 3. And when you plug it into g of x, you're going to get 6. Clearly, g of x, the cubic, is higher on this interval. When you plug in 1 to f of x, you're going to get 1. And when you plug it into g of x, you're going to get negative 8. Clearly, f of x, or the quadratic, is higher on this interval. Since you have 2 intervals, we're going to need 2 definite integrals. So we're going to have the interval from negative 2 to 0. G of x is on top, so we're going to put g of x first, and then f of x. Then we're going to add the integral from 0 to 2. F of x is on first, up is higher, and so therefore first, and then g of x is lower, so therefore second. When you combine like terms and then integrate, and then plug in the numbers. Let's see, 3/4 times 16, that's going to be 4 times 3, which is 12. This is going to be negative 12. So we've got negative 12 plus 24 plus negative 12 plus 24. So let's see, it's going to be 24. And again, that 24 represents the area of the bounded region between the cubic and the quadratic. Okay. Now this one's kind of interesting. This one, the equations were written in terms of y. So when you go to graph this, 3 minus y squared, you're going to have a point at 3, and then the parabola is going to go to the left, just like on a quadratic with an x, like 3 minus x squared, it would go down, so to the left. And then we have the linear function that could be rewritten as x minus 1 equals y. So I'm going to call this one f and this one g. Okay. From our graph, we can clearly see that the intersections happen at the point 2, 1 and the point negative 1, negative 2. Since we have our equation as x equals, we're going to do everything in terms of y. So we're going to look at the intersection at y equals negative 2 and y equals positive 1. When you set the two functions equal to each other and you move everything to the same side, this does factor into y plus 2, y minus 1, so we get y equals negative 2 and negative 1, or positive 1. Then for figuring out which function goes first in your definite integral, instead of going which one's higher, we're going to go which one's like more positive or further to the right. G of x, the quadratic. Oh, I mislabeled them apparently. So let's rename. This is, this one is f, and this one is g. Okay. At any rate, the quadratic is further to the right. Okay, so then we're going to look at the definite integral. The y values go from -2 to 1. The quadratic is further to the right, so we'll put that first. And we're subtracting the linear function, y minus 1, or y plus 1, so we're subtracting, dy. When you combine like terms, you get -y squared minus y plus 2. And we've already integrated one very similar to this, same antiderivative, etc. So the area is going to be 9/2. Okay. When you have this one, when you graph it, we've got a quartic, which is the red graph, and the quadratic, 1 minus x squared, is the blue graph. It also intersects at 3 points, like we've had a couple problems do. But instead of writing an integral from -1 to 0 and then from 0 to 1, we can write a single integral. The reason why this is true is because both of these functions have even symmetry. So the area from -1 to 0 and from 0 to 1 are equal. Therefore, to write this as a single integral, we're going to have the area equals 2 times the area from 0 to 1 of, when you combine like terms, x squared minus x to the 4th. For this one, if we graph it, we've got the cubic in red, x cubed, and the linear y equals x in blue. And this integral won't actually give the area of the shaded region. If you plug it into your calculator and you integrate it with your calculator, you'll see that that gives you 0. There's two big reasons for this. The first reason is that both of these functions are odd functions. So when you do the integral from the same number, negative to the positive of the same number, the area is going to equal 0. On top of that, the function further away from the x-axis is y equals x. So when you integrate, you should really have x first. And when we get the area, we're just going to look at, since these are the same region, which is one's positive and one's negative, we look at 2 times the integral from 0 to 1 of the higher function minus the lower function. This could also be easily written as 2 times the integral from -1 to 0 of x minus x cubed dx. The x is still going to be first because it's further away from the x-axis. We also, when we talk about area between two curves, this area should count as positive even though it's underneath the x-axis, because we're just talking about the area between two curves. It doesn't matter where it is. Okay, and then we have sine and cosine, and they intersect many different times. We've got here, 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 and all of these regions end up being equal area. So I'm going to pick to go between pi over 4 and 5 pi over 4 and just look at what is the area of this region. Okay. We've already picked our interval, and sine of x, the blue function, is on top in this interval. So our integral is going to go from pi over 4 to 5 pi over 4 of sine x minus cosine x. The antiderivative is negative cosine minus sine x. And we plug in 5 pi over 4 first, and then pi over 4. And then from our unit circle, negative cosine of 5 pi over 4 is negative negative square root 2 over 2 minus negative square root 2 minus negative square root 2 over 2 minus square root 2 over 2. So when you distribute all the negatives, we should get a whole bunch of positive root 2's over 2. When you combine like terms, you're going to get 4 root 2 over 2, which is 2 square roots of 2. Okay. Our last example comes from the first two parts of the 1998 AP Calculus free response question. Let R represent the region bounded by the x-axis, or y equals 0, the graph of y equals the square root of x, and the line x equals 4. So there is region R. The area is going to equal what we did definite integrals before. We've got the area from 0 to 4 of the function square root of x dx. And you don't really have a minus 0 because, well, minus 0 is nothing. So that integral is just 16 over 3. The far more interesting part of this free response question was part B. We want to find some value h, somewhere in here maybe, that divides region R into two areas of exactly the same. The way you would split this up is you could say the area from 0 to h of the square root of x. Since it's supposed to be exactly half, we can take half of 16/3, which is 8/3. We already know what the antiderivative is, and we want to evaluate from 0 to h. And we need to set that equal to 8/3. At this point, it's just an algebra problem, and we can solve and get h equals the cube root of 16. I know this was a lot of examples. I hope this video helps. For those of you who are on the show choir trip or doing math sci shadowing, if you have any questions, feel free to email me or see me when you come back to class, and I will talk to you guys later.